So we're going to talk a little bit about LNG and refrigeration. This video is going to be about the refrigeration loop and then understanding certain concepts that are important to understanding LNG. So this is the pre-sequel to the LNG video. Okay, so there's a couple different definitions that we need to understand. We have boiling point, which is the temperature at which a liquid becomes a vapor, right? We have dew point, which is going to be the opposite. It's going to be the temperature at which a vapor becomes a liquid. You ever wake up in the morning to go catch the school bus or let your little chihuahua out in the grass, and even though it didn't rain the night before, the grass is wet? That's normally referred to as dew. So what's actually happening is the temperature drops at night low enough to reach the dew point, or the temperature, the moisture in the air becomes liquid or water. Now that we know what boiling point and dew point are, we need to understand how they correlate with hydrocarbons. So lighter hydrocarbons are going to be hydrocarbons with fewer carbon and hydrogen atoms. We're just referred to it as the number of carbon atoms in the hydrocarbon molecule. C1 through C2, the lattice of the lights, right? We'll refer to C5 plus when we get into LNG, that's your heavies that you don't want. So the lighter the hydrocarbon, the lower the boiling point, okay? So when you think about adding heat, you think easier to achieve, right? Which is accurate. But when we get to dew point, the lighter the hydrocarbon, the lower the dew point. You always think higher, harder to achieve, lower, easier to achieve, but that's not necessarily the case when it comes to dew point, because the dew point of LNG, for instance, methane, is negative 260. So when it comes to dew point, negative 260, and let's say you're heavier than ethane, right? Your C3 plus, that's going to start condensing around 120. If it's all of these combined, okay? It's going to start condensing. So lighter hydrocarbons, lower dew point. Which one's harder to achieve? Negative 260 or negative 120? Which number is higher? Negative 120 is higher, right? So it's going to be easier to achieve. So heavier hydrocarbons, higher boiling point, higher dew point, and higher freezing point. The dew point and the freezing point are easier to achieve. We're talking negatives. Lighter hydrocarbon, lower dew point, lower freezing point, and lower boiling point. So the lower boiling point will be easier to achieve, but when we're talking negatives, the lower dew point and freezing point are going to actually be harder to achieve. To understand LNG and certain concepts behind it, we must first understand how pressure affects a gas and how pressure affects a liquid. When molecules are in vapor form, they're constantly in motion, okay? So this is going to represent a container with gas molecules in it. Remember, they're constantly moving around. Let's follow out some molecules in our low pressure container. It's going to go good, and then hit one, okay? Hit one, hit the container wall, hit one, hit one, hit one, right? Okay, so as you increase the pressure of your gas, the molecules become closer together. So the amount of time it takes to hit the next one is going to be a lot shorter. The distance between them is going to be a lot less, right? So ding, 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 right? As we increase the pressure even more, ding, 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 right? The molecules are hitting each other faster and harder. So I'm going to do this little exercise to explain it to you. So I have my little beach ball, and if I throw my beach ball from back here and let it bounce off the wall, okay? Now, if I compare that to throwing it right here, the same strength, it's going to travel a lot further and go a lot faster. So that's what's starting to happen with these molecules. They're going to be traveling a lot faster and harder and then bumping into the next one. Now, each time the molecules, regardless of the pressure, each time a molecule hits another molecule or the sidewalls of a container or whatever it may be, it's going to create friction. Now, we all know that friction results in heat. Let me zoom back in. So with gases, when you increase the pressure, more friction, the molecules are going to be moving more aggressively, faster, hitting each other harder and more often, causing an increase in friction. So higher pressure on a gas is going to result in higher temperature. Lower pressure on a gas, less bumping into each other, right? So less friction, lower temperature. To understand how pressure affects a liquid, we must first understand what has to happen in order for liquid to boil. Okay, so all liquids have a vapor pressure. Okay, that's going to be represented by this guy in the yellow shirt. In order for boiling to happen, the liquid's vapor pressure must become equal to or greater than the external pressure exerted on it. The external pressure exerted on it is going to be pushing down, holding the liquid in liquid form to where your liquid cannot escape in vapor form until heat becomes strong enough to overcome the pressure exerted on it. Okay, so as we add heat, heat increases the liquid's vapor pressure, right? So he's getting stronger, but the external pressure is still holding him down because he hasn't become equal to him yet. So still not boiling, but as we add heat, that heat increases the vapor pressure of the liquid. Okay, next up, we added enough heat. We got it to the boiling point, right? And we're able to boil because our vapor pressure became equivalent to the pressure exerted on us. He was able to overcome, and the liquid was able to escape in vapor form. So when it comes to how pressure affects a liquid, if we go from, instead of having this, we increase our external pressure, make them even bigger, or increase the pressure. Now he's going to have even more heat energy than normal applied, so that way his vapor pressure becomes equal to the external pressure. So higher pressure on a liquid is going to increase the liquid's boiling point. It has to get hotter in order to become equal to the external pressure. So the temperature at which it boils is going to go up because the amount of heat needed to make it reach the equivalent of the external pressure is going to go up. Another way, let's say Big Macho, our vapor pressure now is this small. So we're decreasing the external pressure, right? Well, that ain't going to put no resistance on our liquid's vapor pressure, our yellow shark gas, and he's going to be able to overcome that easily. So if you decrease the pressure, you're actually decreasing the boiling point. So air conditioner loops and refrigeration loops work the same way. They may have a little bit of a different terminology. They may be designed a little differently, but they're going to still have the same components doing the same thing. The refrigerant in a refrigeration or air conditioner, the Freon or whatever it may be, its dew point and its boiling point are very close together, and it's very close to ambient temperatures. Okay, so this is our basic refrigeration loop. We're going to always start with our compressor when we go through our refrigeration loop. So as P-Tech students, we already know that our compressors increase the pressure of a gas, right? So we already know it's going to be gas leaving our compressor. We know the pressure is going to be higher. And we've just recently learned how pressure affects the temperature of a gas, right? Higher pressure, higher temperature. So leaving our compressor, we're going to have a vapor. I'm going to put V for vapor. We know it's high pressure, right? So I'll put HP for high pressure. And we know that higher pressure, higher temperature, so it's going to be hot. So in an actual refrigeration loop, it's going to be a reciprocating compressor or positive displacement compressor. Okay, so for an air conditioning cycle, your condenser is your outside unit for your air conditioner. It works kind of like a fin fan. It's got a fan. It's blowing ambient air on your tubes. So we know as operators that condense means turn a vapor into a liquid. So we know leaving the condenser, it's automatically going to be a liquid. Your heat exchanger should not be changing the pressure of your gases or liquids. So it's still going to be high pressure, and we know it's not hot anymore. So we're going to refer to this as cool. Okay. The reason we don't say cold is because cold and warm is going to be somewhere else. So this is going to be cool. All right. Now we're going to our expansion valve. We're going to refer to this as our JT valve because that correlates with LNG. Okay. So the JT effect is rapid drop in pressure equals rapid drop in temperature. Or the JT effect is very relevant when it comes to LNG. So rapid drop in pressure equals rapid drop in temperature. I use this keyboard air duster as my physical examples for my students in the classroom. So I normally have them shake it up and down to feel that it is actually liquid in here. But when you spray it, it's vapor, right? Also, I'll spray it a decent amount of times and have them fill the can. It actually does get colder. The JT effect, so now that we know it's liquid in here, right? You ever notice when you read a keyboard cleaner, it says caution, contents under pressure? Well, the way they're able to keep it in liquid form in here is because they're increasing the pressure. And again, how does pressure affect a liquid? It increases the boiling point. Higher pressure, higher boiling point. Lower pressure, lower boiling point. When it leaves here and goes to atmospheric pressure, well, drop in boiling point, right? So drop in pressure, drop in boiling point. So to help further explain the JT effect, rapid drop in pressure equals rapid drop in temperature. This is one of the things I use. So you see how it's ice forming on here? Rapid drop in pressure equals rapid drop in temperature. Another analogy I could use is when you just exhale on your palm. It's warm, right? Well, when you blow, you're restricting flow on your upstream side of your restriction. Is going to build pressure downstream of that, or after, it's going to make it colder. So when you blow, all of a sudden it's cold coming out or cool coming out now. That is an example of the JT effect. You're restricting flow, which is going to drop the pressure leaving. Okay. So your JT valve, all it does is restricts flow, which creates a pressure drop. Your pressure is going to build upstream or before it, and the pressure is going to drop downstream. With refrigeration cycles and air conditioners, they may call this the throttling device, but we're gearing this more towards LNG. So we are liquid going in our expansion valve. Now, another thing to keep in mind, a refrigeration cycle or an air conditioner cycle is not the same as an LNG liquefaction facility. In an LNG facility, we are trying to cool to get to dew point, right? So we'll use the JT effect on gas to rapidly drop its temperature in order to get closer to the dew point of LNG. In this scenario, it's a little different. Normally, you need heat to boil, right? But in this scenario, we're dropping the pressure so much that the boiling point drops and it actually starts to flash off with that JT effect. And instead of using heat energy like from an external source, it's going to use its own energy to boil, which is going to rapidly drop the temperature. Okay, so we're actually going to be a liquid vapor mixture leaving our JT valve, and we're going to be cold now because JT effect is rapid drop in pressure equals rapid drop in temperature, right? And JT effect again, rapid drop in pressure. So our pressure is going to now be low pressure. Now our evaporator, what word is in the evaporator? Vapor, right? So we know it's going to be vapor leaving the evaporator. However, the purpose of the evaporator is not to turn the refrigerant into vapor, okay? The purpose of the evaporator is to cool your room air. So let me see if I can show it. If you look up, you'll see this right here. That is our air intake. It's pulling our room air up in, okay? And it's actually blowing it over the evaporator coils. And then when it leaves the evaporator coils, it's going to come back through our vents and it's going to be cold air going back into the room. So the purpose of the evaporator is not to turn our refrigerant back to vapor form. The purpose of the evaporator is going to be for the refrigerant to absorb the heat from the room or fridge air to cool it off, okay? So you have warm room air going in and cold room or fridge air coming out. Your coils are full of super cold refrigerant. And when I say super cold, I mean frostbite cold, okay? And it's going to blow the air onto that. The refrigerant is going to absorb the heat from the room air and then send it back out cold. So from there, we know that it's going to be a vapor, right? Remember, like I said, exchangers shouldn't change the pressure of your process. So it's still going to be low pressure from our expansion valve. And then it is going to be warm. So not as hot as leaving the compressor and not cool in liquid form like leaving the condenser, but it's warm and in vapor form.